All right. Good afternoon, everyone. Welcome to our second lecture, real lecture this semester. It's good to have everyone back here after the long weekend. I hope you had a good time relaxing at home. Hopefully you did other things than just work or study, as you should have. Before we begin our lecture today, I just want to say have a quick poll there regarding our setup for the live streaming of the lectures. As I was saying before we actually just started, to those of you who were there, I'm still having a lot of trouble with Zoom showing the same setup that I have on the Twitch live stream. And I am seriously thinking of changing that setup a little bit. The main purpose of having the Zoom meeting is basically so that we can have our private voice conversations and chat so that it doesn't go into the public live stream that is recorded and available on YouTube for later consumption. So I don't know. Any ideas? I suggested maybe using Discord instead of Zoom, or we can just keep using Zoom as is, but without videos at all, and just have it as an audio chat kind of on demand if somebody has a question maybe to ask, or if I'm going to pose a question to you folks here so that we can hear my question. Problem with that might be there is a little bit of lag between the live stream on Twitch and the Zoom call, of course. I think somewhere between 5 to 7 seconds, depending on how busy the internet connection is that day. So I might just keep it as such, but I'm happy to accommodate or hear any other ideas or thoughts. Anyone has any strong feelings towards or against any kind of setup? Mm-hmm. Okay. Okay. All right. So I wasn't suggesting that I'm gonna remove the Zoom link or Discord or whatever else completely. I'm just suggesting if Zoom is preferable perhaps, or if you want to use Discord, or it just doesn't matter as long as there is some way of having this voice communication or interaction between everyone in the class and myself. This is going to continue. It's just a matter of which technology probably works best. So maybe then what I will do is I'll just keep the Zoom link as is, since I have it already set up and I know it's working and so on. But I'm just not going to have my video enabled on the Zoom call. That will be the only difference, since it's just using bandwidth that is not what I'm actually want to share with you here. And it seems from the chat that people, at least those who are sending messages, are okay with that. Okay, so I guess we're gonna keep it as that, unless something goes completely wrong with Zoom during the semester, and then we can have our maybe another alternative like Twitch, Discord or something else. Okay, I'll keep it at that, and let's start actually to dig right in to our lecture today. So in today's lecture, we are going to talk about intra-procedural analysis, and this lecture is just not going to be one lecture. This is probably going to be the longest topic that we're going to discuss in the course. So we're going to have this topic maybe span at least 2 lectures this week, and maybe another lecture from next week on Tuesday, but we'll see how it goes. So the next topic we're going to discuss is intra-procedural analysis. So previously in the class last week, we discussed the following topics. The main thing that we discussed early on in the course was that static analysis by definition is undecidable. Let me pause here for a second and ask you a quick question. You can respond on the Zoom chat or the Zoom voice chat as well. Why, or if you remember, why is static analysis undecidable? What makes it undecidable? User input, yes. So, yes, Mohammed. Right, so user input. So you don't know exactly, depending maybe on the user input, as a couple of you have said, which path the program will take. So you cannot at compile time or statically without running all possible execution paths to figure out what those possible execution paths could be. And we're actually going to see today first hands-on, we're going to see today the first problem that we're going to face in static analysis when we get to generate control flow graphs, as I'm going to show you later. So we talked about static analysis being undecidable. We've seen a few sample analyses like constant propagation, like dead code elimination. And we have seen some intermediate representations and the different trade-offs between having a high-level intermediate representation, such as a control flow graph or an abstract syntax tree, versus a lower-level intermediate representation, such as Java bytecode or Gimple. And we also have gone through a case study of Java and Android and how both architectures can be compiled down to an intermediate representation such as Gimple, so that the SUT analysis framework can operate on both of them. So in this topic, in today's topic, moving on for the next couple of lectures, we want to answer the following question. We want to answer the following question as such. So given a method, you just have one method, a method of some sort, or an application, a piece of application code, and you have some interesting property like, did I close all the file resources that I opened? And you want to put these two together into an analysis of some sort. You want to write an analysis of some sort that can answer the following question. Does this property hold at a given statement S in that method, that input method, or not? And all what we're going to discuss today and on Thursday and at least part of Tuesday is going to be the foundation of being able to answer that question. So what could be those interesting properties that we have been talking about today and in the last lecture as well? So one interesting property could be, is this variable still used later on in the program or not? So looking at a program, looking at a method, I want to ask the following question. Is variable v or variable a, for example, going to be used later in the program or not? And this type of analysis is called live variables analysis. And it's a very important actually analysis specifically to compilers to determine how it's going to allocate registers perhaps to some variables, and also how to reason about certain compiler optimizations that are going to be performed to improve the performance, the runtime performance of the application. So this is live variables analysis. The other property that could be interesting as well to write a static analysis for is something like, can this code ever execute? We have seen this in the last lecture. So this is dead code elimination analysis or dead code analysis. So this is used quite a bit in optimizing code size in generated code, typically used in mobile application development to make sure that your code or your application is going to fit in whatever restraint or resource restrained or constrained environment that is the mobile device that your app is going to be deployed on. Another question that is also interesting property to answer is, can a certain pointer ever point to null at any given point in the program or given any kind of user input in the program? This is obviously called a nullness analysis because you want to determine whether a certain pointer is null or not. But why is that analysis important? Because maybe you don't have a language that has runtime checks against accessing a null pointer like Java does, for example. So in Java, if you access a null pointer, it will just throw a null pointer exception at runtime. And maybe your language doesn't have that, so it might cause an error, or maybe you just want to avoid these runtime errors altogether, so you want to capture them at compile time so that you can eliminate any kind of runtime abnormalities or runtime problems when you deploy your application. Another example of analysis that we have seen in the last lecture is this file handle ever closed? So this could be answered by a type state analysis that tracks the state of objects in your program and figure out whether they are in an acceptable state or not. So all these are different types of properties that I mean by interesting property that static analysis can answer to you, and these are the analyses or the formal names or the official names that you will see in the literature that and try to answer these questions. So let's have an example. So let's consider this piece of code. It's a Java-like language. There's a bunch of assignments before a while loop, and inside the while loop there is an if-else statement, and after the if-else there is an assignment statement, and then you're printing out some value out there. So the very first thing that we want to do to this code is the following. Or before even that, we want to answer the following questions. First, we want to answer the question, which variables may hold a constant value in the program. So I want to track values that are constant in the program, even though that I'm using variable names, but maybe the value is constant. I want to know that. And second, which values do these variables exactly hold? So not only do I want a yes or no question or a list of variables that would hold constant values, but I want to know exactly what that constant value is, because then maybe I can use it in further optimizations later on. Okay, so these are the two questions I want to answer. Now let's see how we're going to build an analysis that will answer these two questions here. So the first thing I want to do whenever you write your static analysis as a static analysis engineer is you need to figure out what is the intermediate representation that you're going to use. And here I chose control for graph to build a control for graph for that method or for that code snippet here as my IR. So in the control for graph, all what we're doing is, instead of having the high-level language constructs there, we're going to expand them into a little bit higher abstraction. We are going to still have nodes as statements. So here each statement like this one, for example, z equals 3 is a node, x equals 1 is a node. But you can see here that the while loop, there is no while in that conditional node here, but rather in that node we are going to have the evaluation of the condition of the loop, which is x is greater than 0. And then based on the true-false execution of that loop, of that condition, whether the condition is true or not, we're going to have to either execute the body of the loop, so in this case this is the true branch, or if it's false, we're going to exit the loop and go to the end of the method. So assuming here that we take the branch of the loop is true, we're going to execute the if-else statement. So again, the condition x equals 1. If it's true, we're going to that branch. If it's false, we're going to that branch. And then depending on that, y is going to have a different value based on either branches. And then after that, whatever the value of y is, we're going to assign 3 to x. So this is this value, this statement here. So after the if-else statement. And then we're going to print out y, and then we're going to go back to evaluate the condition of the loop. And this is what it means, that you're going to loop while x is greater than 0, and we'll keep on doing that on and on and on until we're done, until the value of the condition of the loop is false, and then we're going to exit the loop. Okay, so this is good. So we were able to create a control flow graph for that input code, and then that will capture the runtime behavior of the program. And remember from the previous lecture that the control flow graph may have some or may model some behavior of the program that will never happen at runtime, because it's always going to be an over approximation of that runtime behavior. So it's not going to be exactly what the application will do at runtime, but rather an over approximation. Again, because static analysis is undecidable, so we try to over approximate what result it should be generating. Okay, so now that we have this control flow graph, we want to answer our questions. Which variables from all those variables here, z, x, y, and so on, would hold a constant value, and what would that value be? So to do that, before we actually develop the analysis, let's actually just do this on the control flow graph. And here I would actually like some help from you. So I'm just going to pose the question and just answer through voice chat on the Zoom meeting that we have. So I'm just going to give you some help there. So at every single statement, right before that statement, meaning right before I execute the code at this statement, I want to know exactly what is going to be the value of x, y, and z. So I'm just giving you here the fact that before this code actually starts executing, the value of x is going to be 0, the value of y is going to be 0, the value of z is going to be 0. So now my question is, after that statement, z equals 3, how those values of x, y, and z would be changed? So what would be the value of each one of those variables? Just looking at the control flow graph. Sorry, say that again, Mohammed? All right. So after, okay, good. So after executing that statement, x will stay 0, y will stay 0, nothing has changed, but z now is going to be 3. So what about the second statement? X equals 1. What would happen to those values, x, y, and z? All right, Robert, x is going to be 1, y is going to be 0, z is going to be 3. And I assume these dots are commas rather, right? Probably. Okay, cool. All right, so after that, after this statement, x is going to be 1, y is going to be 0, and z is going to be 3. And the main reason really is that that statement only affects, like this statement x equals 1, only affects the value of x. It doesn't affect the value of y or the value of z. Now we have x is greater than 0. Would anything change the values of x, y, and z? Does that statement, executing that statement, does it change the values of any of x, y, and z? No, it doesn't, right? Because it's just a condition, it's an evaluation of a condition, it doesn't have any side effects. So this is another term that you're going to hear quite a lot in the course from now on. This statement doesn't have any side effects on the values that you have in your program, which means it doesn't modify or change or add or delete any kind of fact about the program so far. It just evaluates to a certain value that you are going to use later on. So again, x after that statement is going to be 1, y is going to be 0, and z is going to be 3. So now, assuming that we are going to execute the body of the loop, so now we are going to evaluate that condition x equals 1. Again, the same thing. again the same thing. But after that statement, we're not going to change the values of x, y, and z. They're going to be the same. But now, assuming that we're going to take this branch here, y equals 7. So after executing that statement, what would be the values of x, y, and z? Just following the control flow of the program. One, 7, and 3. So x is going to be 1, y is going to be 7 because I changed the value of it here, and then z is going to be 3. Yes, exactly. And then after that, when I execute x equals 3, or if I take the false branch, because y now is going to be z plus 4, so now I can say, well, y is going to be 7, z is still going to be 3, and y is the variable y is going to be 7. Well, because z I know is going to be 3, 3 plus 4 is going to be 7, so I can say directly that y is going to be 7. And at that point, x is also going to be to be 1, and I should actually change that in the slides. By the way, I'm going to make all these slides that I'm going to use in the lectures available to you, and I'm going to have a link to them on eClass, so you don't have to worry about that. So I'm going to make them available in both whatever format I'm using here, which is Keynote, but also I'm going to make them available as PDF, so in case you want to take notes on them during the lecture or something of that sort. Okay, so now we have x equals 1, y equals 7, and z equals 3. So all these values so far are telling us that up to that point in the program, and here we have a question, what if y was not initialized as 0 at the very beginning? This is a really good question from Ridwan. So the question is, what if the value of y here is not 0? What if it's something I don't know? Well, I wouldn't be able to say here that y is 0. I wouldn't be able to say here that y is 0. And I wouldn't be able to say here that y is 0. And here I will be able to say that y is 7. Here I will be able to still say that y is 7, right? Because I'm overwriting whatever value that y had. But probably the more interesting question is something like, well, what would be a more interesting question? No, not really. I mean, they're all going to be overwritten at one point. A more interesting problem, rather, that we were going to have is if we don't have a value of y that is overwritten, and I just assume that it is going to be initialized with 0 at the beginning. And at that point, I cannot make any assumptions about y because I don't know what the initial value of y is. So, for example, if at that point here, let's say here, I have a statement that says x equals y plus z, right? So at that point, what's the value of y? Well, I don't know. What's the value of z? Well, it's 3. 3 plus I don't know just means that the value of x is I don't know. So you can't answer that question for x at this point in the program. Does that answer your question, Ridwan? Cool, awesome. So now what happens now? So now we are executing that statement x equals 3. Before executing that statement, we have x equals 1, y equals 7, z equals 3 on that branch. Here we have x equals 1, y equals 7, z equals 3 on the other branch. So we just got lucky that on either branch, the true or false, the if or the else branch, we have the same set of facts about x, y, and z. Now when x is equal to 3, I'm going to override that. So now x is going to hold the value 3, y is going to hold the value 7, z is going to hold the value 3. And then after that we're going to print y, which is fine. And then we're going to go back and execute the body of the loop, assuming that the body of the loop evaluates to true. And we'll keep doing that as we go. So now when we enter that condition of the loop again before we evaluated, we are going to start with a new set of facts, which is x equals 3, y equals 7, and z equals 3. And then after that, we're going to go in through the body of the loop, x is greater than 0. Again, it doesn't change anything about the input facts. Then the output of that, I'm just going to put the value that is going to, the value of interest basically there. So z is going to be 3 at that point, x is going to be 3, and, well, actually I should have all the facts that I'm looking at. And y is 7. And if I take the true branch here, that's going to make y is equal to 7, z is equal to 3, and x is equal to 3. But if I take the other branch, again, y is going to be equal to 7, z is going to be equal to 3, and x is going to be equal to 3. So remember that in this iteration of the loop, the values of x, y, and z are different than in the previous iteration of the loop. Specifically, the value of x and z. Y is pretty much, so far, is the same value, but x and z, they change the values every iteration of the loop. And now after that, we assign x to be 3, and we'll keep on going, and so on and so forth. So now after the statement, x is 3, y is 7, and now z is 3. So this is great and everything, but if you notice, we had to go through a couple of iterations of the loop, and we just stopped right there. We should have, in order to get the actual result, we should have gone through every single iteration of the loop. That's one thing. The other thing, this is not an automated process that we have done. What we have done is that you basically got a paper and a pencil. Maybe it's a fancy paper given the iPad and a fancy pencil given the Apple Pencil, but still it's a paper and a pencil solution where you have to manually go over every single statement, every single edge on the control flow graph, and figure out what are the input facts, what are the output facts about the variables in the program, what the values are, and do some computations and do things basically on paper. This is not really interesting. Like, you can't possibly write an analysis. You can't possibly do that for a large program, right? So we've just did that for a simple while loop that has one if-else statement. So imagine doing that for a substantially large program such as, I don't know, what is your favorite Android application, or maybe a mobile application that you have on your cell phones? Maybe some social media app like Facebook or Wikipedia or Google Meet or Zoom or something. That will take quite substantially longer than just the 10 minutes that we spent on this simple example here. So this obviously doesn't scale. So what we want to do instead is we want to do this using some automated approach and some automated process. But in general, the idea is that we want to enumerate, or to get the result, we should get, naively, we should get the solution where you execute all the paths in the program, and you sort of meet or join the result, you sort of find the solution that is the meet over all paths. So find all the paths in the program given the if conditions, the while loops, the back edges, the go-tos, and so on. So you're going to have multiple paths in the program, and you want to find the meet over all paths in the program, or the MOP solution. And that solution is the solution that is going to give you the answers to your questions that your analysis is aiming at. So what do we mean by that? Assuming again that we have the same control flow graph. So this is the same example that we have just seen before. And I just need to watch out for the time. So in about 5 or 7 minutes, we're going to have our break. So please remind me on the Zoom chat if I forget that. So now we have our control flow graph as before. Nothing has changed there. So what do we mean by the meet over all path? So basically, the meet over all path would be all the paths that would have to path that would enumerate the potential runtime behavior of the application. So here we have a path that goes to x equals 3. I can go to x equals 3 using that path, or I can go from the false branch, right? Or I can go in the second iteration of the loop, take the true branch or the if branch, or I can take the true branch, but in the third iteration of the loop I take the false branch, and so on and so forth. So all these paths I have to account for. So all the combinations of the true and branch, the true and the false branches, or the if and the else branches in the application, I should account for. And then enumerate them for all possible iterations that my program may have. But how do we compute that meet over all paths solution? Because remember, we just said at the beginning of today's lecture that if static analysis is undecidable because you don't know what the user input is, you don't know how many, how possibly your program may react to those or may execute those on those user inputs, so you cannot possibly determine at compile time what are all the paths that your program may take. So this solution is actually not feasible to compute. It's uncomputable. But if you want to compute that path, if you want to compute that solution, this is how you formally would write it out. So we're going to read this formalism together so that you understand what I'm talking about, because we're going to see a lot of it, especially in the next couple of lectures or so. So this says that for all statements S, such that S is an element of the set of statements, or the list of statements that we have, the meet over all paths at a certain statement, so if you are at a single statement like the x equals 3, if you want to get the meet over all paths from the beginning of the program up to that point, up to that statement in the control flow graph, is basically the meet, and this is not a union, this is a meet operator, and we're going to get into that later in today's lecture, maybe, but maybe in the next lecture, most probably. And what we're going to do is that we're going to approximate the behavior of the program from one statement to the next using functions. And we're just going to use those functions and compose them together along each path, and then compute the meet over all paths of these functions. So every statement would have an effect or a side effect on the facts that represent maybe the constant values of the variables or whatever property you're interested in. So we're going to represent those as functions. Along each path of interest or path that we have in the program, we're going to compute the function composition along that path from the beginning of the program, and this is S0 or statement number 0. So this is the beginning of the program, up to the statement S that I'm currently computing the meet over all path. For each path, compute the composition of the functions. You're going to end up with a humongous function for each path. You do a meet over all those functions, and then you're going to get your meet over all path solution. So I is going to be the initial value. Thanks, Akalanka. I was just going to answer that question right now. So what is I here in this? I is going to be the initial value that you start your analysis with. So for example, this goes back to Ridwan's question when Ridwan asked, what if y is not initialized at 0 at the very beginning? So how do you tell your analysis what initial values for variables before it begins? So this is what this I is. This is the initial value that the analysis would give to operate on or to start with its analysis. The FP is the function composition for that path. So all those functions, we just give them a unique name in static analysis called flow function. And why are they called flow function? They are called flow functions because they are functions that represent the flow of data or the flow of information from one statement to the other. So the flow of data or information here, what kind of information or data are we talking about? Well, I'm talking about the facts that the analysis is interested in. The fact that x is 0, or y is constant, or z is a null pointer, or f is a file that has been closed, or a file that has been opened, or a file that has been created. Whatever fact that you are interested in tracking throughout the program is going to be represented in this flow function. And like I said, like everything else that you're going to see in this course about static analysis, this is an uncomputable problem in general, and you can go back to the paper by Kam and Ullman from 1977 when they discussed the post-correspondence problem and how this affects the fact that the meet over all path solution is basically uncomputable. But this, again, this all boils down to the fact that we are doing things at compile time without running the program, and we cannot possibly run every single run of the program using whatever inputs that the program may have. But still, even despite all that, we still need to make some decisions regarding how we can over-approximate that runtime behavior of the program. And this is exactly what we're going to do in not only in this lecture today, but this is basically the essence of static analysis research. How can you over-approximate whatever property or whatever interesting property that you want to answer questions about in a way that captures as much as possible of the runtime behavior of the program. So this is what the meat overall path solution is, but it's uncomputable, so we have to defer to something else. So let's consider this piece of code here, and that's probably going to be my last example before we go on a short break in the middle of, in the midpoint of the class. So this piece of code is a bit different than the code that we have seen before. So here we have read n, so now we have some user input, right? So that I don't know exactly what n could be, something that I read from the user. And depending on that n, I will execute either the if portion of the branch or the else part of the condition. And then I'm based on the values of a and b, I'm going to compute the value of c, and then I'm going to print out or write c maybe to disk or to the screen or something. So now I cannot possibly know what the value of n is, even statically. So now let's see how we can over-approximate that. Again, the control flow graph, before I do anything else, I need to create the control flow graph of the program. So here I'm going to read n. This is the first statement. Here I'm basically condensing some of the computations. So here I'm just saying if n is less than 0, that means I want to execute the true portion of the branch, then go to L1, which basically goes here. Everything now is implemented as conditions and go-tos. We don't have while loops or jumps of any sort. Everything is go-tos at this point. A equals 1, then B equals 4. If it's false, then A is going to be 2, and B is going to be 3. And then if the else branch is done, I'm going to jump to L2, which is basically the exit, which is that C equals A plus B, and then I'm going to write C. So before I do that, I may actually implement a further simplification or a further summarization rather of the control flow graph. So I might actually create something called a basic block graph. So each node now is not necessarily a single statement in the program, but each node represents one basic block of the program. So what do I mean by a basic block? A basic block is basically a list or a sequence of statements, right? So it's a sequence of statements such that the beginning of the basic block, such that it doesn't have any jumps or go-tos in the middle of that block. So it's a sequential list of statements. There is no jumps or anything in the middle of the block. The only point in that basic block that you can have a jump or a go-to would have to be the last statement of the block. So you cannot have a go-to in this second statement here. It can only be in the last statement of the block, like in this case here. And the beginning of the block may be a potential target of any other go-to statement in the program. This is roughly what a basic block graph is. So now nodes in that graph, it's basically another simplified way to look at the control flow graph. So now this basic block graph is nodes could be our basic blocks, and then edges are basically the transfer of the control flow from one basic block to the other. And this is what I'm going to operate on. So again, this is yet another intermediate representation that you may think of. So one path could be this path here. So in this path, I'm basically taking the true branch, right? I'm going to execute that A equals 1, B equals 4, and then go to L2. C is going to be equal 5, and then I'm going to write C. So how am I going to simplify or compose or create the flow function that tells me what's going to happen along this path in the program? So first, I'm going to start with the init value, the initial value that I'm going to start my analysis with. Then I'm going to apply that initial value. I'm going to apply the first flow function, which is the flow function of that statement here on that initial value. So I'm going to apply the flow function at the statement read and on whatever initial value. And what does it mean applying the flow function on that initial value? It means you're going to apply a function on some value and you're going to get a value back as a return value of that function. So think of this as any function. It's a mathematical function or a function that you write in any kind of language. You give it some input, you get some output from the other end. And I'm going to give each flow function a label there that basically tells me this flow function is for that statement f read n or fn less than 0 and so on. Now once I have this, I move on to the next statement. So what I'm going to do is I'm going to use the result of this flow function as an input to my next flow function. Right? So I'm going to compose. This is what I mean by composing functions. So you start with your initial value, make it as an input to the flow function of the first statement, it will give you some output. You make that the input to the next flow function, which is the condition n equals 0. You make that you take that output, you make it the flow function of the next statement, which is f equals a, f of a equals 1, and you take that the output of that flow function. You make it the input of the next statement, which is f b equals 4. You take that output, you make it as an input, you pass it as a parameter to the flow function of that statement, c equals a plus b. And you take that output, you make it as a flow function, you make it as an input to the last flow function, f right of c. So this is how you compose the flow function that would represent this path from the very beginning of the program, or S0, up to the point of the program, which is the end of that control flow graph or basic block. And this function here will now represent the full path in sort of a mathematical formula that you can use in program analysis and stack analysis to reason about. I'm going to stop right there for a few minutes. Maybe we are going to reconvene again at perhaps 1:15 maybe. So a couple of minutes, 4 minutes of a break. When we come back, we're going to quickly summarize that slide here and move on to see how we're going to compute the paths of the flow functions of other paths as well, and then compute the mean overall path for the program. I'm going to still be available on the Zoom chat during that break. So if you have any questions, you can ask me there. But I'm not going to deliver any further content in those few minutes. Make sure you stand up and stretch your legs and walk around. This is a long class, and this break is kind of important in the middle of the class. So we're going to reconvene in a couple of minutes. So question here, off topic, does functional programming by definition makes program analysis more predictable because of the restrictions on mutations? Well, it depends. I mean, things being mutable or not mutable, you can still have a functional language that where some methods have side effects, like in Scala, for example. You can still have functions that have side effects that goes beyond the boundaries of the method. So the question here is, like in functional programming, or if you program everything as functions, does that make program analysis more predictable? What you probably are asking is, if your functions are purely functional, so meaning that they don't have any side effects, does it make it more predictable? It might make generating summaries or computing the values maybe a little bit easier, just because you know that there are not going to be any side effects beyond the boundaries of the method. But still, as we're going to see when we get deeper into the topic, and specifically when we talk about lattices and fixed point iterations, you're going to see that this is not necessarily the case. Even if you are talking about one single function, still predicting or computing the value of an analysis or the analysis result is really tricky. I mean, even with that example that we have so far, we're not talking about multiple functions. It's the same function, but you have multiple paths within that same function. So it doesn't help with the language being functional to make the analysis result more predictable. It helps in certain aspects, but not in the general sense of things. I hope that answers your question, Mohammed. All right, cool. So let's continue with our lecture today. So before the break, we went through converting the control flow graph into a basic block graph, and then we computed the composition of all the flow functions along the path of the true branch, starting with the initial value, which became the input to the first flow function, and the output of which became the input to the next flow function, and then the next flow function, and then the next flow function, and so on and so forth, until we got a functional composition of all those flow functions of statements along that path that will eventually give us the result of which is basically the result of our analysis at the end of the program, starting from the initial point of the program. So great, so now we have a formula basically that represents that path, that true branch, or the path that goes through the true branch of the if condition. Now we're going to do the same thing for the other branch that we have. So we're going to do the same thing. We're going to start with the init, and then the init is going to be the initialization or the argument to fread, which the output is going to be the input to fn less than 0. But now we are going through the flow functions of the false branch instead of the true branch. So this part here is different because it represents a different branch. But eventually, we're going to have this output of fc equals ab as an input to fwrite c. So now we have the flow function, or the composition of the flow functions that represent the false branch. We have the one that represent the true branch. And now if we want to get the path summary of the whole program, we have to meet or compute the meet of these two branches, of these two paths of the program. So again, the meet over all path. In this case, we only have two paths in the program because we don't have any loops in there. So it made it a bit easier to actually at least be able to express it using these formulae here. So the true branch meet the false branch, and then that would be the analysis result that we are looking for. But to be able, actually, given this mathematical formula that we computed here, to be able to actually have something that we can compute, maybe writing a program for or writing an algorithm for, we are going to introduce a monotone framework. So we are going to introduce the first framework in static analysis that you're going to get experience with in this semester, which is called the monotone framework. So what is the monotone framework, and how can it help, or how does it help in computing a solution to the meet over all path problem, and how does it actually make it computable when we just said a few minutes ago or almost an hour ago that static analysis is undecidable. Finding the mean over all path solution is an uncomputable problem, and how we can get around that. So let's find out together. So the purpose of actually having any kind of framework, and specifically this monotone framework, is that you want to have a general structure of computing solutions that could be configurable by whatever or customized to whatever the needs of the developer is. This is basically the generic definition of what a framework is. We have something that provides a general solution or a generic solution that still could be customized and personalized depending on the needs of the developer. And the monotone framework is no different than that. So you have a uniform evaluation algorithm, right? You don't have to specify and make the algorithm that will solve the analysis problem specific to a specific analysis, like constant propagation, like nullness analysis, like dead code elimination, like a pointer analysis. You have the same algorithm that will solve the problem, but you can plug in certain customizable points in that algorithm. So flow functions is one, initial values is the other, and so on and so forth. That will enable you as an analysis developer to reuse the same algorithm over and over again, but for various different analyses. And that's exactly what the monotone framework provides here. So how does it do that? So the combination of the flow functions and the initial values and other things with the uniform evaluation algorithm would give you a particular static analysis. So how do we do that? So there are 5 different parameters, few set of parameters, excuse me, that you can parameterize or customize the monotone framework with in order to get the result of the analysis. First, you need to decide, is your analysis going to go forward from the beginning of the program to the end of the program, or is it going to go backwards in the control flow graph, meaning from the endpoint or the return statements of the program or the method, because now we're talking about just one method, all the way back to the beginning of that method. And this is basically a Boolean parameter. It's either true or false. Is your analysis forward? No, then it's going to be backward. There is no other option there. The second point is, what is the analysis abstraction that you're going to use? So what do I mean by that? I mean by that, what are you trying to compute? What is your analysis interested in? Are you interested in the states of the objects in your program, so a type state analysis, or are you interested in constant values, constant propagation, or something else? So for that, we're going to use a new structure that probably some of you may not have been introduced to before, called the lattice. And that is the thing that we're going to discuss in our lecture, perhaps on Thursday. So we're going to use a lattice to decide or to define the analysis abstraction. The third parameter is, we want to decide or we want to compute the effect of each statement on the input information. So we just have gone through that a few minutes ago. Does anyone remember what is the name of that thing that describes the effect of each statement on the information or the property that we're interested in? Something that we just computed, the composition of flow function. Yes, Taylor, exactly. So here we're gonna get actually not just one flow function, but we're gonna get a set of flow functions. We're gonna have a flow function for every single statement along the way, and then we're gonna somehow compute the composition of these flow functions, and we're gonna go into more details later about how we're gonna do that, and then represent the effect of each of those flow functions on the statement, or on the flow function of each statement on the information that we're computing for the analysis. Then, of course, since we're going to start this analysis from somewhere, we need to give it some initial value to bootstrap the analysis itself. So we need to initialize the analysis before we start. And for that, since we have a lattice that represents the analysis abstraction, we have to get the initial values for that initialization as values from the lattice itself, because every element of that lattice, every value on that lattice would represent a possible value that whatever property we are interested in answering may have. So if you're talking about nullness analysis, then lattice values would be null, not null, for example. If you're talking about constant propagation, possible lattice values could be 1, 2, 3, -5, 10, 100, a million, and so on and so forth. A merge operator. So remember, we had a flow function or a composition of flow functions for the true branch, another composition of flow functions for the false branch. How do you merge them together? How do you compute the mean overall path? And for that, we are going to have a binary operator on lattice values. So a binary operator because it takes two inputs and then it generates an output. And it has to be defined over all possible pairs of inputs on that lattice. So now this lattice value here, again, this is another question, or this is another parameter that is related to lattices, or the lattice that we're going to use to abstract the analysis or define the analysis abstraction. So let's take those parameters as we go. The first question is forward or backwards. Should our analysis go forward in the control flow graph, or should it go backwards? So what determines that? Basically, what will determine that is the following. So before I actually go into that, I'm going to stop for a minute here maybe and just pause for a second and make sure that if anybody has any questions so far about what I discussed in today's lecture, before we go any deeper in those parameters and what do they mean and how we will configure them in the monotone framework. Just give a thumbs up on Zoom if you're okay, if you don't have any questions. Because silence usually, I don't know what to make out of silence. Might mean that you just can't hear me, or maybe my question didn't come across. All right. All right, cool. So far, so good then. So the first parameter that we can configure from the 5 parameters is forward or backwards. So should our analysis go forward in the program, or should it go backward in the program? So what determines that? So basically, forward is you want to compute information about the past. So think of it this way. The direction of the analysis being forward or backward depends on where do you want to compute the information about. If you want to compute values about the past, then you should go forward. This is where you're coming from, because you have to compute the values, or you have to be coming from the point in time where you already know the information. So if you want to compute values about the past, then you should go from the past to the future. You should go forward in the program, right? Because here's where you know the analysis result, in the past. However, if you want to compute information about the future, you should be going backwards. Again, why? Because if you want to know something in the future, then you should sort of go from the future backwards to the current point in the program to be able to know the answer. Because you cannot know the answer if you haven't been at the point in time, at the point of lifetime of the program where this answer is available. So if you want to have something about the past, then you should go from the past to the future, meaning forward. If you want to know information about the future, then you should go from the future to the current time, meaning backwards. So what do I mean by that? So let's have some examples. So I'm going to ask you or give you the analysis and then its official name, and then we're going to decide together what the direction of that analysis is. So the first is, which values does a variable carry? So what are the variables that the variable may carry in the program? And that analysis is called constant propagation. So at a certain point in the program, you want to know whether the given variable in the program at this point is constant and which value it holds or not. So which direction do you think this analysis is? Is it forwards or backwards? And why? Not just tell me what the direction is, but tell me also why. Is it forward or backward? Anybody? Come on, there's only two options there. Pick one. Forward. Why is it forward? So it is forward because we want to know about the past of the variable. Well, okay. You want to know what the value of the variable. Okay, so you want to know the constant value that the variable may have hold. Yes, that's it, precisely correct. So it's going to be a forward analysis because I want to know so far in the program. What do I mean by so far in the program? Meaning, given the past up to that point, what is the value of that variable? Okay, great. So next question. Which variables will still be used, right? So the name of that analysis is live variable analysis. Or liveness analysis. So which direction do you think this analysis is? Is it forward or backward, and why? It is backwards because we are looking for future variable values. Are we looking for future values? So indeed it is backwards, but I'm asking more about the reasoning why it is backwards. Like here I want to know which variables are going to be used. Period, right? Like I don't know their future value. Like that's not my main interest, but I am interested whether they're going to be used in the future. And the key thing here to look at is basically will still be used. When does this happen? It happens in the future. So if it's something that's going to happen in the future, it has to be a backwards analysis. So this is going to be a backward analysis. So what about, will this file handle be properly closed at the end of the program, perhaps? this analysis here is again a type state analysis. We have seen this before. Which direction do you think this analysis would take? Backward or forward? So in this analysis here, by the way, if you have questions or you're just want to brainstorm the answer, just feel free to just unmute yourself and talk to me, or just send a message on the chat, so that we can all benefit from the discussion that is going on within the class. That's really the main purpose of having this Zoom meeting there. So which direction do you think this type state analysis would go? I'm interested to know if a given file handle will be properly closed or not. Seems like I did not understand the previous slide. So the previous slide has little to do with this one here. Oh, you mean, sorry, the direction of the analysis. Okay, so I'll get to your question, Mohammed, just in a second. So Taylor, backwards, we want to know if something will happen in the future. So that's correct. It's going to be a backward analysis because it's something that will happen in the future. So to determine what's going to happen in the future, you have to go from the future back to the past. So let me go back to the previous slide here. So this is the slide that Mohammed, you mentioned that you didn't quite get what I meant there. So what I mean here is the following. Assuming that you have two directions of the analysis that can go. Either go forward, meaning from the beginning of the program till the end of the program, meaning here the program is basically one method because we haven't talked about multiple methods yet. So do you start from the beginning of the method to the end of the method, or backward as in from the end of the method to the beginning of the method to run the analysis? So what is the order of statements in the method that the analysis should start scanning through? Does it begin from the beginning, from the start to the end, or from the end to the start? So what determines that is the following. What determines that is what is the type of information your analysis is interested in computing or asking about. Am I interested to know something that will happen in the future? Meaning if I'm at this statement here, like z equals 3, am I interested to know whether z is going to be used at this statement or not, right? And if that's the case, how would I know that z is going to be used at this statement? So there's only one way for me to know that. I have to be at this statement, right? Basically, I am at this statement here now. I'm at this point. So this point where the squarish kind of structure is. And if I want to answer the question here, whether z is going to be used in the future, I basically have to visit the future, figure out, oh, here is z is going to be used. No, it is not going to be used. Then I go back. So once I do that, it means that I have to go to the future and then go back to be able to answer the question. That means my analysis has to be a backwards analysis. I have to go in the reverse direction of the statements in order to be able, the order of the statements that I have to scan them with have to be a backward order, have to be the reverse order. How do you do that? We're going to get to that in a minute. However, if my question at this point is the following, let's say, what is at this point, for example, what is the value z constant value or not, right? So if I'm at this point, I want to know whether x is constant, whether y is constant, whether z is constant. Excuse me. How do I answer this question? The only way I can answer this question is if I go to the past statements, all the previous statements, and figure out whether the values of x and y and z are constant or not, and then come back to where I am to be able to answer that. So that way I'm going from the past statements to the current point. So that's why the analysis has to follow the same direction, which is forward. So if the only way to answer your question is to come back from a future statement to where you are to be able to answer it, then this is the direction of the analysis that should take. It's a backward analysis. If the only way to answer your analysis question is to come from a previous statement to where you currently are, then this is the direction of the analysis that should take, which is a forward analysis. Some analyses might be formulated as either forward or backward, depending on how you want to answer the question. But this is the general way to determine the direction of the analysis. Does that answer your question, Muhaymin? Okay, cool. So we have seen a couple of analyses. Some are forward, some are backward. Now this is another question here, another analysis here. So another analysis for you folks here is, has a variable been defined in the program or not? So the name of that analysis is possibly defined variables. And why would you be interested in such an analysis? The main reason is you want to know, for example, again, this goes to one question that we had earlier in the class today, whether y would have been initialized or not when we did some the constant propagation analysis that we did earlier in the class. So you want to know possibly whether some variable is defined or not. So which direction you think this analysis should take? Is it a backward or a forward analysis? And why, of course? Forward, since we want to know the history of a variable. A second forward, because we're checking in the past to see if it has been defined or not. Cool. So we have two forwards. Anyone saying backward? Another forward, because you'd have to go back and then walk up to that point. Okay, so you have to figure out whether this has been possibly defined up to that point or not. So indeed, this is a forward analysis precisely because of all the reasons you mentioned in the Zoom chat there. Because I have to go back in the program to figure out, has this variable been defined before or not? If it has been, then this analysis would say yes. So if I have to go to the past to answer the question, then I will take, and then I will come back from the past to that point, then this is going to be the analysis direction that I should follow from the past to the current point. So these are different types of analyses that can have to be defined as either forward or backward analysis. So this is the first answer, the first parameter that you can configure in the monotone framework, the analysis direction, forward or backward. So what do I mean by that again? Again, assuming this piece of code here, you have, so this is an example of determining the analysis direction. This is a password, so it's private information, and you're printing out P2, and let's say I want to track whether I may leak the password to the outside world by either printing it out on the screen or perhaps just sending it over the network or something. Well, I can determine this by saying, I'm going to do a forward analysis because I can say, does P2 or did P2 ever hold a value that's the password in the past, right? So if I want to determine whether P2 holds the value of a password, I can formulate my question as, has P2 ever held the password value in the past? So to answer that question, I have to go to the past, all the points that happened before, and then figure out from that point, at every single statement, does P2 ever got assigned that password value or not? So if this is going to be the direction that I have to go, so it's going to be a forward analysis, right? But I can also write this question down in sort of the reverse direction. So I can say, can this password here ever be printed in the future? So rather than doing this, let me use a different color. So can this password here ever be printed in the future? So how do you determine that? Well, I have to go to the future, find out all the print statements, and from there on, come back to that point and then say no or yes, it could be. So if I have to go to the future and come back to that point, then I have to go in the backward direction. So I have the same analysis that tries to answer the same question, or rather to answer the same question. I can have an analysis that does this in a forward direction, but I can also have an analysis that does this in a backward direction, depending on how you formulate your answer, how you formulate your question. So sometimes, as we're going to see in the course, it might be easier to have your analysis be a forward analysis if possible. In other cases, it might be easier to have it backward if possible. In other cases, you don't have the option. Your analysis has to be forward or backward. In some cases, just by design of how your analysis operates, it has to be backward, even though there is a forward formulation or a forward direction for it that is capable of answering the same question, but just given the current circumstances and the current constraints in the environment that you're going to deploy your analysis in, your analysis has to be operating in a backward fashion. So let's say you're going to do a backward analysis here and you want to compute information about the future. So how you do that? Basically, all what you do to do a backward analysis is you just reverse your control flow graph. So basically reverse the direction of all these edges here that you have. So all those edges, just reverse their direction and then do a forward analysis on that reversed control flow graph. So if you think about it, I don't need to write two different analysis algorithms again, right? Like you remember the monotone framework, you have one analysis or one algorithm that provides the solution, but you can configure it in such a way to support multiple different configurations. So this is the first use of having this configurable nature in the monotone framework. You can still have the same analysis algorithm. You can still have the same algorithm that computes the solution, but to be able to get a backward analysis, you just reverse the direction of all the edges in the control flow graph and then do the same kind of forward analysis on it, and you're going to get your backward analysis result. That's why a control flow graph may have multiple tails, because you may have multiple return points or endpoints. So here you have a return statement, here you have the end of the method, and it can of course have multiple heads as well, because if you reverse the control flow graph, those tails will become the heads of the control flow graph. So you have to have a data structure that can support this kind of having multiple starting points or multiple heads and also multiple tails in the control flow graph. So if the control flow graph may have multiple tails, it may also have multiple heads in the backward direction of the analysis. So we are almost close to time. So I think this is actually probably a good point to stop here and just reflect on what we have discussed in the class so far in the remaining couple of minutes. And in the next lecture, we're going to start with analysis abstraction and lattice theory and how we can use what do I mean by a lattice and how we can define it both formally and practically, and how we can use it to determine what values my analysis may give to variables in the program, and how it's going to enable us to configure the remaining parameters of the monotone framework. Does anyone have any questions so far about this class, this lecture, how the course is going, how the course is going to go in the future, or any questions whatsoever that you may have? All right, no questions. Any comments? Is everything else clear in how the course is gonna run for the remainder of the semester? Don't forget about assignment 1, which is due at the end of this week on Friday. I've seen already some questions posted on the eClass forum. Feel free to reach out to me or Ifaz on the eClass forum or by email if you have any questions about the assignment. The rubric is there for all the assignments, not just assignment 1. And make sure that you also look at assignment 0.0 and 0.1, which is basically selecting your project partner or paper seminar partner or partners. And they have, I think the deadline for each one of them is still later this month, but just keep an eye on them. Otherwise, I'm just going to do a random selection for the groups for your partners. So if you want to work with someone, please make sure that you form these groups early on. So if there are no further questions, I think that will be all for today. Thank you all for joining me today. It was great seeing most of the class actually in the live stream so far. And if you have any questions, please don't hesitate to contact me or Ifaz at any point. And I look forward to seeing you all on Thursday. Thanks, everyone.